Recording is on.
Okay, now it started again. So the idea here is there are two hash tables, right? As I said, immediately we need to add the starting node into into the depth, right? We added a with 0 and a with null. This is exactly what we did here, right? A with 0 here, a with
A
null
with
value, right?
yes.
Now we have the while loop, same thing. While q is not equal to empty and deq the node, and immediately we are checking is that the node you want to reach. As soon as you deq the element, you want to check is that the destination node that you want to reach. If that is the case, just break the loop. We no need to process the adjacent nodes of the end node. Okay, but if it is not, we will process the adjacent nodes. For each adjacent node or next node, we are checking is part of the hash set or hash path. No, then we are adding the node as a key, and the value is the actual node you just dequeued from the queue. That is the source node, right? So
Okay.
basically you can reach this next node from this node. Okay, and
Okay.
immediately we are enqueuing into the queue, and then we also checking is it part of the depth. If it is not part of the depth, definitely it will. If it is not part of the hash path, it won't be part of the depth as well. So hash depth, so we are putting in the hash depth. Here is the node. How to calculate the depth? We need to get the depth of this node plus 1, right? Add 1 to the depth of the parent, basically.
Okay.
Is exactly the way we did, right? So how we got the 2 here? We got the
This
depth of the
node,
D.
yeah,
So
plus
F
one.
equal to 2 because F came from G, right? So basically, depth of G plus 1.
Yes.
So how we got the 3 here? So E is equal to 3 because depth of D is 2. For 2, we added plus 1.
Okay.
So that's what we are exactly doing. Basically, hash depth of the node, the current node what you are processing from the queue, plus 1.
Plus one. Okay.
Okay, this is the complicated. This is only, I would say, only these 3 lines or 4 lines. This is only the crux of the whole logic. Otherwise, we are simply other thing is same thing, right? You are adding into the queue, dequeuing from the queue, and for loop of every adjacent node is same. Only difference is adding the parent, and the other difference is
The
putting the
depth.
depth. Basically, calculating the depth. This is
Yeah.
the only complex piece. Now you're done. So once everything is done, once the whole queue is done, okay. Now let's see shortest path. Okay, I should put after this. Basically, this one should be here. What I'm saying here is, let's say hash path does not contain the end node. That means, let's say I'm asking you to find, there is one more node called x here. I'm asking you to find from a to x.
Mm.
Okay, what happens is, from you start from a, all the elements will be added to the hash tables, but this particular node never be included in the hash tables because it is not reachable.
Mm.
There is no train from A to X. There are two
Yes.
stations called A and X, but there is no train from D or E or C, even though they are very nearest stations, but there is no train station. There is no train path. So, what do you say? So, finally, the X never be in any of these hash tables, right?
Mm.
That's what it is. If the particular end node what you are looking, if you are looking for a X, if you are looking for a station X is not part of the hash path, that means end node dot data node, basically end node is X. X node is not connected to the given start node A.
Yeah, yeah.
It, it will say like that. Basically, it's kind of error checking. If you are, it's not error. Basically, it's a unreachable condition, right? You've given the two paths. It's showing yellow for you. Is it okay? Can you see my screen now?
Yeah, yeah, I can see.
Okay. So this is the check. Yeah, this is a kind of a check we need to do before proceeding. If we don't find the element in the hash path, we will simply say there is no path.
Not connected.
Simply return.
Okay.
You just need to return because there is no path. Now, if there is a path, it will come here, right? If the particular end node is already in the hash path, that means and you reached end node. Shortest path from A to F is print the path. This is another interesting. As I said before, we need to print the path, right? So and also printing path requires only this one, right? Only this table.
Okay.
This is the only one we use for printing. What we used for printing this one, right? We used this particular hash set, the first one, correct?
Mm. Yes.
And we also need the end value. You started from F, and you're seeing, hey, what is the destination of F? It is G,
Okay.
right? See, here is the G. And then what is the destination source? Sorry, not destination. From where you came. So G. Okay, you printed G. Now how G came? G is from A. So A. So we need this hash map in order to print the path. That's why we are taking this hash map, and also we are taking the end node. So last node. So that is the print path method. So what are we doing here is we are sending the end node, and we are also sending the hash path. Let's look at this. This is the first time we are using the recursion after so long, right? We use recursion in linked list or other algorithms, right? So this is another place where we are using recursion. Look at this. So we got the first node. Sorry, this is the end node, and here is the hash path. And if n is equal to null, return. Otherwise, print path, hash path of n, and hash path. This is complicated. Basically, what are we doing is we are recursively going to the same method and giving the parent. Did you understand here?
Yes.
It is a little bit complicated. Basically, you got F right now, you got F, and we are calling the same method using the hash path of F. That means we are calling the same method print. Let's say this is print of F, and then we are calling print of G because we are getting the value of F. What is the value of F? Value of F is, okay, let me go back to the, yeah, value of F is G, right?
Yes.
Value of F is G. So now we
G.
are calling, hey, print G, but we don't want to print G yet. We are again calling what is the value of G. So if you look at algorithm again, we are not printing. Printing is only at the last step, but we are calling the print path again with value of G. What is the value of G?
Value of G is A.
Yes.
A.
So A. So we are asking to print A. Now we are taking next step. Okay, what is the value of print path? What is the value of A? What is the
Null.
value of A?
Null.
Null. Now, okay, print null. Print null.
If
Now
it is null,
this tuple exists. If it is unequal to null, it will return. Return means it return back to the stack, and then it will print A because that's what we just processed, right? So it prints A first, it prints A, and then it prints G, and then it prints F. So it will print the path in a reverse way. No, it will print the path in a correct way because we are calling recursively, and we are printing after the recursive call. If
okay.
you remember, in order, pre-order, post-order, this will help you to solve that. In order, pre-order, you remember that, right? In order, pre-order,
Yes.
post-order.
Yes, yes, yes. I remember.
Similarly, this is same thing. Similarly, we are not printing yet. We are calling again, and finally we are printing.
Okay.
And the depth. Finally, we printed the path, and depth of the path is simply hash depth of a node. Simply, this is very easy. You can just simply go here and give me the depth of f. This is the depth of f. Simple. It's very straightforward, straightforward, value.
Okay.
So the path is a to g, g to f, and the depth is 2. Fair
Okay.
or depth or distance, this is 2. These are the two, these are the two inputs of this whole algorithm. And I ran the algorithm before, and here is the thing. So look at this. Shortest path from A to F is AGF. See, it
Depth
printed in a
is
correct order, right? Because of the recursive function.
function.
Shortest path from A to F is AGF, and the depth of the path is 2.
Two short path. G2D is
Shortest path
G2D.
from G to D. G to D. Let's look at G to D. G to sorry, G is here. G to D.
GFD. Yeah, GFD. G.
GFD, because actually, yeah. So shortest path is GFD. It can be GACD also. There is another path, right?
Yeah,
GACD, but that
GFE.
free.
GFED also.
Yeah, GFED also there, but the value is 3. But
Yes.
shortest path is simple. GFD is the shortest path, simply 2, right? And the next one, shortest path from E to B. E to B. E is here and B is here. So EFB, right? That's what we got. EFB. Same thing. 2. Okay, that's the biggest algorithm. It's a
Yeah.
complex
It's a
logic.
complex thing. Yeah.
So, any questions or is it clear? So, basically, there are two main functions here. First one is display shortest path, and the second one is the print path. These are the two main important, logic here. So, the rest of the thing is all set up. Basically, just creating all the nodes and connecting the nodes, and finally, I just called all these methods. Shortest display A to F,
Okay.
short path. It's all set up. Yeah. So, okay, I hope it is clear.
Yes.
So I send this algorithm. Okay. Any questions?
No, Suresh, I have to work with this algorithm before asking
Yeah,
question.
it is
I
complex. It
understood the
definitely has
algorithm, but it's complex.
exactly. It requires analysis. You need to understand again, and you also need to practice. This is something I did 3 years or 4 years ago. I practiced yesterday. I looked at the algorithm because I did not even remember like what I did, how I did. So it took a while for me. I spent more than 40 minutes or 35 minutes to 40 minutes to understand hey how to explain. So not only just understanding, right? I need to a little bit of practice how to explain. I don't want to show the code directly, and I want to come up with an idea, putting in a graphical way and
But
explaining the things. I
this
hope.
solution, we have to derive this solution, right? How did you come up with this solution, Suresh?
I don't remember. I did 4 years back. Maybe I referred a couple of websites or YouTube videos, or somebody explained. I don't remember. Like this is something we discussed in one of the Saturday meetings. So
Okay.
I think he's the person. He the Eugen is the person. He gave kind of homework actually. This is a question after discussing. He works for Google. He's a senior super senior most engineer in Google. We use it to meet every Saturday, and he explained this algorithm. I think maybe he explained
The
the
solution.
solution. Yeah, this is something like this particular algorithm I did 3 years ago. I stored a PDF. Maybe I found the solution from this PDF, but this PDF is not opening. I don't know.
Okay.
Maybe somebody removed this PDF. Maybe I found the I found the algorithm here. So yeah, you can search for something like this shortest HORTS shortest path in unweighted, unweighted graph. There will be a lot of algorithms. See if you can find any good videos or any another, another way of doing it. See, Geek for Geeks. There is a lot of people contribute here. I don't know how the process. I don't know how the way they are doing. They might be doing a different way. There is C sharp here. Not look like just we add edges and yeah, they will also do a different. I think they since they are following a different method, it
Okay.
will be different algorithm because a graph can be represented in a different way, right? As I said
Yes.
before, the graph they represented in a different way here. The way is, see, add edge. What is this? Add edge 0 to 3. Creating a graph given above diagram. Add edge function takes adjacency list. Oh, they are using adjacency list. See, so it's a completely different representation of the graph. So that will definitely change the way they did this. See, it's almost like similar logic. Look at this. They are taking the queue. They are also taking visited kind of visited
Okay.
Boolean. Yeah.
Okay.
So yeah, it's everybody does in a different way. So yeah.
Okay.
Okay. Yeah, I think let's stick to one way of doing it. So rather than following different methods, that see
Okay.
the using adjacency list is one way, and even a matrix. I told you right. Some people will use the matrix. Matrix representation of the graph. Graph can be represented in multiple ways. So when you represent in a different way, the way you tackling is also different, right?
Okay.
Yeah. So he also explained in a really good way. Let's look at, yeah, maybe you can also look at this.
Aqua architect. Okay.
What's that?
Well, I'm just uh, noting the URL. It is good.
Sure, sure. Yeah, yeah. See, there are nice videos as well. Let's see if any of those will give you more idea. So, but anyway, if you understood this whole the way I explained, you can just practice the same way and let me know if you have any questions. Hey, I did not understand this particular line, so I would like to know if you have any questions like, hey, I did not understand how this is working, how what is happening here. We can definitely not only here any algorithm that we discussed before. I'm happy to revise again and explain the logic again. Yeah.
I'm working on the last week algorithm still. Once I complete
Nice,
it, if
nice.
you have any questions, I'll let you know, Suresh, and I'll sure make
Yeah,
sure of this
anytime.
concept by next week. Thank you.
Awesome, that makes sense. Awesome, cool then. Okay, that's it for today. I will send the recording and I will also send the link in a couple of hours. Okay.
Okay. Thank you. Thank you.
Awesome. Yeah. Good night. Yeah. Bye.
Have a great week, Suresh. Bye.
Yeah. Thank you. You too. Bye bye.
Bye.
I'm stopping sharing. Yep. Bye.